All right, welcome to the third to last Water Quality Wednesday. This Wednesday, we're doing water quality best management practices, and we've got a good slate of speakers lined up for you today. We're going to have the Statler Family Farms, Greg LaBarge, and Dr. Libby Dayton as our panelists. And my name is Bridget Moneymaker. I'll be your host today. I'm an OSU Water Quality Extension Associate. I cover Auglaize, Mercer, and Allen County. And then moderating the chat today in the question box will be Bowden Fisher, another Water Quality Extension Associate. He covers Putnam, Hancock, and Hardin County. Speaking of Water Quality Associates, there are two other upcoming webinars that we will be hosting. Feel free to scan this QR code to go to the website to register, or you can also click the link at osu.edu/WQW. Next week, we'll have Peggy Hall talking about Lake Erie water quality litigation. And then in April, we'll be doing a water quality in the Western Lake Erie webinar, which would be great for a good overview on the geology and history of Lake Erie and the Western Lake Erie Basin. Just some general housekeeping. The webinar is being recorded and you will be able to access it on the OSU Agronomic Crops YouTube channel. All the webinars are there. All the webinars we have been doing with the whole college have been there. So feel free to check that out and see some of the other work our colleagues have been doing. Give us a few days to put that up there just as we can clean it up and get it edited for you. For CCA credits, the QR code will be provided at the end. You're going to need a smartphone to scan that, or you can also report missing credits at the CCA website. So after our three speakers, we are going to be having a short Q&A session. At the bottom of the Zoom toolbar, you should see the Q&A tab. I think it looks different depending on which Zoom you have, but feel free to use that throughout the entire webinar. Despite which speaker is going, you can just drop all your questions there and we will collect them and answer them at the end. And you can also use the chat box if you have any questions during or after any panelist. All right, so this morning we have Anthony and Dwayne Statler from Statler Family Farms. They are a family farm who farm about 1,150 acres in Hancock County, corn, soybean, wheat, and a head-to-tail swine operation. And they have dedicated about 243 acres to the Blanchard River Demo Farm, which, if you are unfamiliar with the Blanchard River Demo Farm Network, it's a farm network that consists of 3 families located within the Blanchard River watershed. They were selected by local NRCS and SWCD staff on the criteria that included farms that were receptive to opening their farms to the public, a willingness to share certain financial information about their farm, and their ability to implement conservation practices beyond what they're already doing. So they are also going to be showcasing conservation across different scales of ag operations. So today we've got Anthony and Dwayne on the call. Anthony is going to elaborate on a few specific conservation practices that their farm is currently utilizing, including variable rate, drainage management, soil sampling, and nutrient placement and side dressing. So I'm going to continue sharing my screen, and then Anthony will be giving you a quick overview of explaining the practice, their experience using it, and some of the water quality benefits that they have seen. So first up, we've got drainage control structure. There's about 3 slides for this one, including this graphic. So Anthony, I see you've unmuted, so I'll mute myself and you can go.
Yeah, well, thanks everyone. A little bit about the farm, family operation up here in Northwest Ohio, as Bridget said. We've got several different water control structures that are on our farm, along with the manure that we use, variable rate, and et cetera on that. The first slide you got up here that we've got through on the farm, over on pretty much all of our acres on the home spot, is the drainage control structures. And what that allows us to do is be able to shut that water off, or be able to hold some of that back. We know by using the drainage control structure that we can be able to hold back nutrients that are leaving our field. The drainage control structures on our farm are pretty much closed 7 to 8 months out of the year. The only time that we open these control structures up is when we're about a month away from starting to plant. Once we get everything planted, and depending on the crop that we've got, we will go through and close that after we get after we get the crop up. And then as we go through the summer, we're able to hold back some of those, some of the rains that were when we're lucky to get them. With that, then about a month to 2 to 3 weeks ahead of harvest, we will go ahead and open that structure up. And it's not necessarily just open the structure up and all of a sudden you have all this water that leaves our field. The control structure does a pretty good job of holding water back for roughly 7 to 10 days. You can see there in the top right, we have plastic plates that go down in there, and that's what we can be able to control the height of the water at. So during the summertime and pretty much throughout the year, we've got that set about 16 to 18 inches below the surface of the field. That way we're not, we're keeping those roots fairly dry or allowing that to be normal, but we're getting holding back what we can in order for those roots to be able to uptake. When we go through and we do that, like I said, we're able to hold water back for about 7 to 10 days. Once it gets past that, basically the water will still go around our field tile and kind of go through our, soil structure just as God had intended. But in that 7 to 10 days, we're not getting a big flush of nutrients, that's going out. When we don't have, when the tiles aren't running, we're still holding that back. If you look back at the nutrients loss that we've got, yes, we get a big push when we get these big rains on the surface, but subsurfacely, we've always got a constant coffee drip or so coming out of that tile line. So what this allows us to do is kind of be able to stop this coffee drip of water that's going into the creek, and holding back any of the nutrients that we have that are in our field, and still being able to keep them in there. You can see some of the new stuff that we've got there on the left is an automatic control structure that we've got that we're able to get on our iPhone or your cell phone or computer. And you can actually, for those water control structures that might be on the backside of a half-mile field where your outlet is, you can put this type of structure up, and then you can be able to see where the levels are at through your phone and be able to control that instead of during a wet year, or if you've got a big rain coming and you want to get back there and shut it off. You don't necessarily have to be tramping through the mud in order to get to it. You can be able to shut it off by your phone or computer on that. So we've only got one of those on our farm. It's more of a test through the demo farms here. They're still working out some bugs on it. When you get north of Route 30 for us, we're starting to see that maybe we need to double up the solar panels a little bit, just because we don't have as much sun here as what they do, south of Route 30. It just seems to be kind of two different worlds that we've got on that. So going into as I mentioned before, with the hog operation that we've got, we do zone soil sampling and variable rate with our manure. So when we go through and do our soil sampling, we were in 2-acre grids across all of our acres. Now that we're getting a little bit more up to date with the soil sampling, we're starting to do it more in zones. Just basically because we're seeing our different P levels and our different nutrient levels, go with more of a zone type basis. So you can see there on the computer screen on the right hand side of the Ag Leader screen there, you can see the different zones that we've got of us applying manure to a field. So there were basically 4 different types of soil types in this field. And we were able to go through, pull those soil samples and be able to apply the right amount of nutrients that we need. Now, when we apply our manure for the water quality side of it, we're only applying, or we're basing our gallonage and nutrient level based off of P. As we go across the field, when we get the soil samples back, we will be able to plug that into the computer, and come up with a formula on the ag leader side, on the SMS side, to where we can download that into the computer in the tractor, and we can basically be able, the tractor, we can set it at a speed, and it will speed up and slow down the rate of manure that's coming, that we're injecting into the ground on that. We've been doing this for roughly about 4 years now. We're still working kinks out, but it's getting a lot easier now. We've got an older manure tank, so we've got a little bit of hardship on that, but all in all, you can see that we're doing a pretty good job of being able to apply exactly what we need at the right place at the right time on that. Here you can see the strips that we're going through and putting. We were going through and subsurface ripping, trying to take out some of the compaction that we've got there. But the little lines that you can see there are our manure strips that we've got. Our manure tank is a Kohler inject on the back. So our tank is basically running a Kohler about 9 to 10 inches in the ground, and we're injecting about 1 inch to 2 inches right below that. Our tank is 24 inches on center. We feel that that's a really good way in order to be able to get the manure incorporated to where we're not losing that. We do have closing wheels on the back to where we're able to get that covered up to where we're not losing any of that denitrification through the air, as it dries on that. We used to run a Gentil bar on the back and spread it on top. It had its pros and cons. We know that we were never going to, that we were doing a really good job of not losing any manure or anything through the tile as it found wormholes, because it did a really good job of fracturing. However, as we, continue to get these bigger rains, we knew that we needed to do something different. So this Kohler inject allowed us to be able to get that manure and the nutrients underground and get it covered up to be able to utilize as much as what we can of that. A new type of technology or a new style of nutrient placement that we tried here this past year was side dressing corn. Glenn Arnold has done a lot of great research through OSU Extension. This is our corn crop put in to our cover crops. We planted into this with it being green, and then went through and did a post kill on that. As we have been going through and trying to figure out how we can utilize manure to the best of our ability, we've gotten to the place where we're going to try to get roughly 60 to 90 acres a year to where we're going to side dress manure on that. So what that allows us to do is kind of utilize the nitrogen part of our manure a little bit better than what we possibly were in the past, just because we're not putting that on in the summer, and we can be able to utilize the nitrogen part of the manure for us. You can see here in the cover crops, this was a rye and a rape and oilseed radish mix that we tried. We're still continuing to try to figure out the best cover crop mix that we can do. We try not to have, we try to leave some of the crop to where it will overwinter and be able to give us a good ground cover during the spring. However, we do try to do some 4- and 5-way mixes. That way we're able to not necessarily have such of a biomass that we're planting our corn and beans into. That way we're able to get some sun and warm the ground up a little bit.
Since we are a little bit ahead of schedule, I'm going to go ahead and pop this question off for you, Anthony, if you don't mind. Says, with all the flooding concerns in Blanchard watershed, drainage control structures seem to be a potential option, not just for environmental protection, but for flood mitigation. Any comments?
Yeah. It does, as we know, the tiles don't start flowing, right away. So you're able to kind of hold that back on the flooding part of it. as I said, we still keep our levels of the control structures to a spot to where we're not going to damage or hurt the crop. If we get a 4-inch rain, we're going to have water and ponding laying around, no matter what. But if we're fairly dry and we get a 2-inch rain, we know that our soil structures can hold that, and be able to hold that back a little bit, to mitigate, everything running off of those fields. The water control structures are mainly for flat ground. For what we've got now, we do have some other avenues of being able to do that. We've got some float valves that are in some of our that we've tried out that are in some of our tile, and basically as the water continues to back up, those float valves will kind of shut stuff off, to where you don't create so much pressure on our clay tiles that we have within our system, to where we're not having a bunch of blowouts on that. And then as the water goes down in the creek or however, then those floats basically go down and allow the water to be able to leave.
Thanks, Anthony. That was extremely informative. And I forgot to mention at the beginning that since the Blanchard demo farm is a demo farm, you are able to go visit and or talk to them, talk to the other landowners who are participating in that. I'm not entirely sure how their COVID protocols are, if there's different hours or maybe they've slowed down the touring, but this summer I'm sure they'll have some different options for people.
Yeah, last year they kind of slowed down the touring, but anyone that is interested in being able to come out, there's 3 farms that are part of the demonstration farm. They did add a 4th over here by Arcadia this past year, where they're doing some testing. But you can reach out to Farm Bureau or NRCS, and they can be able to point you in our direction.
Thank you. All right, I'm going to turn it over to Greg Labarge for our next section, but everyone feel free to keep posting questions or comments for the Statlers, and we will get to those at the end. Thank you.
All right, excellent. Good morning, everybody. Appreciate you taking some time out of your busy schedules to learn a little bit about some best management practices that we might utilize in nutrient mitigation. I'm Greg Labarge. I'm a field specialist with OSU Extension and work statewide, but focus a lot of my efforts up in the Northwest Ohio area. And that's, the practices we're going to talk about today really fit statewide. Some of them may not fit because of topography and some of those kind of things, but what we're going to talk to today really can work in both the Lake Erie watershed as well as the Ohio River watershed. So just kind of keep that in mind as we're going through the discussion here today. And really what we want to talk about is using soil test phosphorus to identify P risk and then identify some best management practices that link to those different soil test levels. And when we think about soil testing from an agronomic perspective, we have a pretty good handle in relationship to what that looks like and what it does for us in the ideal of utilizing fertilizer and fertility to maximize crop yields, use it in an environmental and effective way from an economic standpoint. And the soil test really does work very well for us in that aspect. There's been a lot of work that's been done in the past looking for environmental tests that measure the environmental risk of phosphorus. There are some tests out there that work, but it's an additional test and really hasn't caught on doing any of that testing because we have that additional or would have that additional cost if we implemented that. But what we have found is really that we can use our standard agronomic soil test as an indicator in relationship to understanding environmental risk. Start here with the soil test relationship to risk of yield loss. And what you have here is really the ideal that we have a soil test level that's increasing across the bottom of the chart, the x-axis going from 0 to 240. Across the y-axis, here we have percent yield reduction. In other words, we're going to see yield decreases at these lower soil test levels. And when we get ultimately, let me get my pen here. So what we have is we have risk that is decreasing as we increase our soil test level. And what we end up with then is a soil test level that will support yields. We work in this crop maintenance range and keep soil test levels in that range, and that from a phosphorus standpoint supports maximum yield. And that follows through with what you see over here as far as our tri-state fertilizer recommendations. When we think about it, though, from a water quality, and in particular dissolved reactive phosphorus losses, that chart looks different as we see that soil test level increase. You know, right here, we've gotten to that point where we're at this 50 part per million for our really standard agronomic and forage crops. That's going to be our maintenance limit. When we've reached that level, we don't see any crop response. As we see soil test levels increase, though, in relationship to environmental losses, over here on this scale, we're seeing an increase in DRP level. And what we're seeing is that as soil test level increases, it increases slowly as far as losses are concerned. And then we reach this point where actually it increases at an increasing rate as far as loss of DRP is concerned. So environmental risk increases as we see that increase in soil test level. And actually, we've gone through a revision of the tri-state fertilizer recommendations, which we can point you to for the agronomic side. And also what we went through in 2020 was a look at the 590 standard. And in that, what was developed was a way to assess nutrient loss risk for both nitrogen and phosphorus, though we're focusing today on the phosphorus side of things. That gives us kind of a scale in relationship to soil test level and thinking about DRP losses. And you see the scale across the top here represented with the 4 boxes. And we're going to kind of go through that today, and you can see how it corresponds to really our increasing risk when we talk about DRP loss here at this point. The only thing that I would caution you with is when we're using just soil tests to establish risk, there are some things that we need to be aware of just as we think about what a field loss might look like. Really, when we talk about using just soil test level, we're just focusing in on the source piece of that and understanding or thinking about how the source of phosphorus in the system is going to increase loss. What we don't, or what we aren't taking into account is here where we talk about the transport piece of what happens in a field, where we're thinking about water moving within that field, carrying that source to the edge of the field, and then ultimately downstream. So really the factors for what actual loss is going to be in a field is going to be a little more complex. And we're going to talk about source plus transport equals that loss. And the source is going to be not only the soil test phosphorus, but any nutrients that we're adding. Transport is going to be affected by some of those inherent characteristics in that field, the soil type, the drainage, what management, including tillage, cover crops, how far that field itself is from water delivery to the watershed. So there are some things that will go or more need to be evaluated a bit further to come up with what that total pounds of phosphorus loss are going to be for an individual field. And there are some tools that we have to evaluate that. We have a tool on Field Ohio. We have a nutrient tracking tool. We have MMP that does some things to evaluate it on a field by field basis. Then we also can use or just simply take water samples at the edge of field to give us an idea of what losses are and really hone in on what an individual field might contribute downstream. The thing that we have with those individual tools is that they take time. And what we find is that if we only rely on soil test results, that our actual P losses for a specific field may be higher or lower than what we have predicted by just soil test phosphorus levels alone. These tools are good at estimating losses on a field by field basis, but they take time. And ask anybody that's written a comprehensive nutrient management plan in the state of Ohio using MMP, and there's a great deal of time that goes into that field by field risk assessment. The ideal maybe a quick screening tool is something that we are able to do with our soil test phosphorus levels. We can start to maybe focus attention with some of those tools with our higher risk fields and actually evaluate them for some of these more costly practices like a P filter that we're going to talk about here in a little bit. And with that, then we also need to recognize that regardless of what field we're working in, that there are practices that will help lower nutrient losses regardless of what soil test phosphorus levels are. And we'll talk about those here in just a few minutes. So let's go back to this ideal of this tool, this assessing nutrient loss risk criteria that we have through our NRCS 590 standard, and look at how we might apply that in looking at our farms and our soil test levels. And this is an example of maybe 4 or 5 fields you might see on your farm, and we have different soil test levels in those fields. We can put them through this soil test phosphorus screening tool, and we come up and it looks more like this as far as what the actual risk of loss is, where we have fields that fall in all 4 of those categories, and we can start thinking about how we need to manage those fields differently based off of that risk of phosphorus loss. And let's focus in on these high risk fields first here, where we're above 120 part per million soil test level. And when we work with these types of fields, these are the fields that have that greatest risk of elevated P concentration and total losses at the edge of the field. This is the situation where we want to identify lower soil testing fields for organic nutrient applications, making manure applications to something that is less than 120 parts per million is better than continuing to apply to these fields. One thing that we'll often do, particularly when we're thinking about phosphorus management, is we'll not soil test these fields, but I would encourage you highly to continue to soil test these fields once every 4 years, follow the standard practice, because we want to manage pH, we want to know what potassium levels are, and then we also want to monitor soil test phosphorus levels, because really our priority in these fields is actually seeing a decrease in that soil test level over time. So we want to use practices that minimize or maximize yield. We want to take the most yield off that we can, because by removing the highest yields, we can also reduce the highest level of nutrient and have an impact sooner on soil test levels. One other thing that we can consider is a crop rotation change. Our forage crops are going to decrease soil test phosphorus levels faster than our grain crops. And that's important when we work in these high soil testing fields. What you see here on the right or the left-hand side is you see a study out of Maryland, and that Maryland study had starting soil test phosphorus levels at 1, 2, 3, 4, 5 different levels up to right here where we're at somewhere around 375 parts per million. And following that line, we end up right here, and we're somewhere around after 15 years of cropping with no phosphorus added, we're still at something like 275 to 300 part per million soil tests. It goes to the fact that our phosphorus is highly buffered in the soil, and soil test levels are going to fall very, very slowly with just crop removal. Here in the state of Ohio, under our current crop yields, we would only expect annual changes in soil test phosphorus levels with no added P nutrient of 2 to 4 parts per million. If you look at any change above that type of removal rate, in other words, if you're actually following a field and you're going from 375 to 275, and it's something more than that annual change of crop removal, really what that's going to do is approximate the amount of loss that we have through drainage. So we do see these higher soil testing fields drop maybe quicker than what we would expect in relationship to crop removal, but what we're seeing is actually a loss of that through tile lines or drainage is where that additional P is going, not in crop uptake. Because of the length of time it's going to take to pull these fields down, these are the ideal fields to think about some of our higher cost water control or filtering conservation practices, because it's going to be such a long time that these fields are going to contribute at a higher rate of loss until we're able to get that soil test level down. On these fields, this is the criteria within the assessment to look at any additional manure applications. And reality is at that very high level above 200 parts per million, no additional P application from what we would talk about as far as our standard either solid or liquid manure applications. And we want to draw down that soil test phosphorus over time. With fields that are in a higher risk category, 120 to 200, what we recommend there is 50% or less P2O5 for the planned rotation applied through manure. And really what we're trying to do there is short-term P applications to facilitate changes in the operation to manure storage or land access. And then we also want to monitor soil test levels that if we're applying manure, that we want to actually see soil test levels decrease. We also have some criteria for ground cover, greater than 50% ground cover or a growing crop out there on that field. So we want to try and prevent the erosion, get infiltration, try and reduce losses by having greater ground cover there. We also want to follow sensitive area avoidance where we're using setbacks, and there is a setback table that you see here. Timing of application, those spring applications made only if applied to a growing crop or a cover crop. And with all of what we're doing from a management standpoint, controlling erosion, sheet and rill erosion at less than soil tolerance, and then no active concentrated flow erosion that's going on in the field. And that would include or be represented by gullies. In other words, that concentrated flow of water to the edge of the field, we want to be reducing or eliminating losses there in this really management of any field that we're working with out there. So that kind of covers those highest and higher risk type of fields, something that's greater than 120 parts per million. We know that there's not a lot of those out in the landscape, but where they're out there, they're potential targets where we need to be thinking about some of these additional conservation practices. Let's talk about that next level then, where we're in that 50 to 120 parts per million, field 3 and 4 that we have here. With those fields, what we want to look at is continuing to not apply any commercial fertilizer source P. We don't have any economic return, no reason to use dollars in relationship to soil test or maintaining or adding to soil test level. When we talk about commercial fertilizers, manure may be used, but we're really still looking at drawing down STP levels over time. So we still want to see that reduction in soil test level. Anywhere we can with these, anything above 50 parts per million, identifying something that's less than 50 parts per million for organic nutrient application is the ideal situation. We also recognize that manure is produced every day, and that at some point in time, it has to go someplace to be land applied. So that's why we still, think about applying manure here. Soil tests continue to do that because we want to continue to monitor that trend. And once again, our target here is to decrease soil test phosphorus levels, so use practices that maximize yields. Once again, consider rotational changes and including forages wherever we can, or maybe a cover crop that we can harvest as a forage in addition to our grain crops. All good practices to try and manage soil test phosphorus levels. In that range of 50 to 120 part per million or moderate risk, the soil test method of evaluating risk would say a rate of application that's less than P removal for either an annual or multi-year crop rotation, less frequent applications at a lower rate, looking at drawdown of soil test phosphorus over time. Here we want to maintain a 30% ground cover, which would be different than the 50% we talked about with those fields above 120. And all the other items are similar as far as trying to look at avoiding sensitive areas, timing of application, and erosion management. In addition to thinking about just managing soil test phosphorus, trying to reduce it, some of the practices that we might put in place on these high soil testing fields are, and that would be anything that's above 50 parts per million, and where we see losses and concentration we'll talk about in a minute of 0.2 part per million or greater. One of the practices that we can use is a phosphorus removal structure. It is a structure that's put at the edge of field, and what it does, it contains a media within these different structures that has properties that remove phosphorus from the water that's filtered through it. Iron slag, there's some engineered materials, there's a variety of different materials that are being tested, but it can be used both with surface water, like what you're seeing here with A and B, and it can be used with tile systems. And it's an engineered system where we run basically water through a phosphorus absorption material. Another option, which hasn't been tested as high a degree, is drainage water recycling, but the ideal of a closed system where water is captured from the field in a storage structure during non-growing or even growing periods where we have runoff, and then we utilize that water during this growing season, either through overhead irrigation or through subsurface irrigation, will reduce the amount of nutrients being lost, and that closed system allows actually those nutrients, whatever aren't lost in storage, to be applied back to the field. Constructed wetlands are another option that we can think about in those above 50 part per million cases. They are best suited where we have the need for treating contaminated runoff and concentrated contaminated runoff, and improve water quality from what's going to exit out of that wetland. Really, these three practices are best suited where phosphorus losses are high. And I actually encourage water sampling to see that we're measuring concentrations at 0.2 parts per million DRP or greater. These practices have a much higher cost. They're in capital investment. Maintenance may be needed on these to maintain that phosphorus removal capacity. I mean, particularly if we're at a very high phosphorus soil test field, 300 parts per million, it's going to be numerous years, and it may actually require either updating or getting that media back in place for like a phosphorus filter several times to make sure that we're removing the phosphorus out of the water that's leaving the site. These also maybe where land is taken out of production. We try and mitigate that a little bit with the removal structures. There's a lot of flexibility as far as how we design those, maybe what media goes into it. that we can make it work in maybe current filter strip areas and the like. Drainage water recycling, we may be able to make up for the lost production by irrigation. The wetlands have wildlife benefits, so there may be for some an incentive with that type of practice. Finally, just want to focus in on these lower soil testing fields, field 1 and 2, where we're less than 50 parts per million. This is where we're going to talk about using the tri-state from a fertility standpoint to recommend the commercial fertilizer or utilize that to select manure application sites. Here's where if we're below the critical level with our soil test level, we increase the risk of yield loss, like what we saw in that opening chart. And the critical level for corn and soybeans is at 20 part per million Mehlich 3. For our wheat and alfalfa, we're talking about 30 parts per million Mehlich 3. Here's where we want to do soil testing for sure. We want to think about a sample area that doesn't represent more than 25 acres. Certainly variable rate applications may be in fields that have a lot of variability across them, and management would be different in different zones. Thinking about variable rate applications in those fields and doing either grid sampling or zone sampling to make that happen. Then certainly standardization of our core collection method, thinking about time of year, sample depth, and also where we locate those core locations with a GPS so that we can repeat and follow trends over time because we have confidence in those soil tests. These fields we're going to be applying nutrient to where we're less than 50 parts per million. So thinking about no more than a 2-year rate of phosphorus, getting that nutrient off the surface, either using subsurface placement or tillage after fertilizer application. And if these fields can be hit with some of our organic nutrients, manure, it's a win-win from the ideal of agronomic benefit and reducing environmental risk. For all fields, regardless of what their soil test level is, the ideal of building soil health, thinking about getting practices that leave more organic matter in the soil are always great. Vegetative filters and buffer strips to remove nutrients and sediment, and then also stabilize soils where we have concentrated flow is important. Where we have blind inlets or where we have pipes like what you see here, where we have really surface water going straight to the standpipe in the field and carrying all that soil with it and out, replacing that with a blind inlet where we can allow that water to filter through. We'll remove and reduce the amount of sediment, and then also we'll remove the amount of total phosphorus for sure leaving the site. We can also think about adding some of those phosphorus sorption materials like what we would have seen in the P filter earlier to these type of field situations and gain added benefit of removal. Drainage water management was talked about earlier, where we are changing the tile outlet. By the amount of water that we hold back, we can reduce the amount of nutrients, in particular nitrogen. Phosphorus, we see reductions, but then we also need to think about what's happening as far as surface water. Does the drainage water, by raising the tile outlet, does that result in more surface flow? We can offset some of the gains that we see in the subsurface drainage from removing phosphorus. So kind of summary here, all fields, what we want to be using is tri-state recommended soil testing practices to monitor soil test levels. Use where we have the need for phosphorus, the tri-state fertilizer recommendations, and apply no more than that amount. Subsurface placement of nutrients, controlling erosion, building soil health, all are good things on all fields. For these higher soil testing fields, you see the things that we talked about earlier in a great deal of detail, and these are going to be where some of these higher capital cost water retention or filtering practices make the most sense, because we can have the biggest impact as far as reducing the amount of phosphorus lost. Here's some useful references that we can share with you. The Ohio Ag BMP Handbook, I would point out, would have a lot more details on the practices that we were just talking about. And we also have a fact sheet that kind of walks through the factors that we were just talking about of soil test level and managing that from a yield and reducing phosphorus losses at edge of field. So a couple of references there to go back to. With that, thanks very much, and hopefully we'll have some questions here a little later.
Thanks so much, Greg. Yeah, the questions, keep them coming. We're collecting a good group here. All right, Greg, if you stop screen sharing, I will hand it over to Dr. Libby Dayton, who will be wrapping up our panelists.
Awesome. Well, thank you. Thank you for inviting me. I'm happy to, this actually works out great because Greg talked about dissolved P, and now I'll talk about erosion. And my bias is that erosion is actually the biggest culprit in terms of most of our water quality problems. I'm trying to get rid of my there. So this is part of, and Greg referenced this earlier, this is part of the On-Field Ohio tool, the On-Field Ohio project that we've been conducting over, a lot of years. And, but today I just want to focus on erosion and how mitigating erosion can help us in achieving water quality targets. So today I just want to talk a little bit about the background of the On-Field Ohio project, show you a little bit of what we're seeing in terms of erosion from our edge of field monitoring, and then, ask the question, is there any hope of improving water quality? So the On-Field Ohio tool actually uses the Tri-State Fertility Recommendations and the 4R Nutrient Stewardship. As Greg mentioned in the 590 update last year, we were approved for use for Ohio nutrient management plans. So as I say, we've completed the work to revise the Ohio Phosphorus Risk Index, and we have developed a tool which I hope will be releasing soon-ish. But the tool, the On-Field Ohio tool, is actually intended to provide a long-term average estimate of field scale erosion and phosphorus runoff loss for both surface and tile runoff. These tools are increasingly being used to judge farmer performance, so it was important to us to get it right. So for our work, we had 29 fields instrumented with edge of field monitoring for, in some cases, just surface and some tile. In most fields, we had both surface and tile. So we had 8 fields in Grand Lake St. Mary's, we had 7 fields in the Scioto watershed, and we had 14 fields in the Western Lake Erie Basin. And of course, I always like to thank our participating farmers. So across our 29 fields over few years, we looked at more than 2,000 runoff events. We looked at more than 14,000 runoff samples, and the farmers were kind enough to give us very detailed information about all their crop managements and rotations. So taking all of this data, we used more of a quantitative rather than qualitative approach to how can we estimate runoff and erosion risk. And so we did this with correlations. So we were relating the edge of field erosion and P runoff that we were seeing to field specific properties and to farmer management practices. So we essentially calibrated our On-Field Ohio tool to the actual measured data that we saw coming off the fields. And we found it was a big improvement compared to the previously used MMP tool in terms of being predictive of actual runoff risk and erosion. So as I say, we found a very strong relationship between our measured values and our on-field Ohio estimated values. And this is for surface plus tile runoff total P. But we do give, the tool does give surface dissolved, surface particulate bound, tile dissolved, and tile particulate bound, as well as also we separate out fertilizer and manure applications. All those are given separately. And then for each year in the crop rotation, and then averaged across the crop rotation. So I'm just showing a little sliver of it today. So what we're going to talk about today is erosion. And one of the things that we found with our measured data is that there was a very strong relationship between a Russell II, and I don't know if everybody's familiar with Russell II, but Russell II is a USDA erosion program that's been around for 60 years. And there was a requirement for us to use Russell II within our tool. So my first question is, well, does it work? And so I was very happy to see that as the Russell II erosion measure went up across our fields, we were significantly related to how much runoff suspended sediment was in our runoff samples. So how muddy were the bottles of water that we were taking out of the samplers? And that was directly related to the Russell II erosion. And similarly, the concentration of phosphorus, the runoff particulate P concentration in our sample bottles were strongly related to our measure of erosion for particular fields. And these dots are all averages of samplers across years, but these are just averages. So then, as I say, we have developed an online tool. We were having some technical difficulties with the tool, with the coding, but I think we've got that worked out now. So I'm hoping to be talking about that shortly. So, you know, for us, the power of the On-Field Ohio tool, because like Greg says, these tools take time to use, and it's a nice thing to do in the dead of winter if you're up to your hips in snow like we have been. Because they do take time, but the power of the tool really is in comparisons. So you can look at your current practices on a particular field, and then you can compare different management scenarios. Maybe you're considering making a change in practices. Well, you could run the tool with, you know, how you're running it now, how you run your field now, and then also with a potential change in practice. And then you can see, well, what would be the water quality and erosion benefit or deficit of a change in a practice. But for now, I just wanted to show a little bit, because I think this is surprising to a lot of people. What is really coming off the farm fields? What did we really see over our years of monitoring? And just as by way of introduction, this is the soil test P of our fields. You can see we had a huge range. Most of them were pretty much within the agronomic range. A couple were just almost deficit, and then we had couple fields that were, you know, really high. So I want to go slow here because these are averages of our surface runoff concentration. So for each field, can you guys see my little pointer?
Yes,
So,
we could see it.
okay, good. So this is field 23, and this is the dissolved P that was coming out the sampler. This is the same field, the same sampler, but this is the particulate bound field, particulate bound P coming out the sampler. And it's the same. Here's field 8, here's field 8 particulate. So we have the dissolved and the particulate for each of our surface samplers. There's no tile samplers shown here because we're just focusing on erosion. And so I think that what's surprising for a lot of people is to see how much particulate P is coming out relative to the dissolved P, because we do hear a lot about dissolved P. My bias is maybe we're not hearing enough about particulate bound P and erosion. And so the other thing about this plot is I did remove any fertilizer or manure application spikes. So this is the baseline situation for these fields. These are averages, and these are across a few years of data. And so the field the field samplers on this plot are arranged from low to high soil test P. So our lowest was probably about 11 to 15 part per million Mehlich 3P. And our highest, I think, was about, what it was at 425. So these fields were at about 100. These are in the 60s, 50s, 20s. So what you see is soil test P doesn't have a huge effect. I mean, the range and the variability in a particulate bound P is kind of runs unto itself, and that's based more on erosion and storms and soil disturbance. But you see the dissolved P doesn't have a huge range usually. It stays pretty tight, and it's completely, almost completely correlated with your soil test P. But your particulate bound P is really much more sensitive to erosion, which is directly related to soil disturbance. So as we can see that the P concentration range and variability of the runoff particulate bound P is generally considerably greater than what we see for the dissolved P. And it probably shouldn't be very surprising, because across the year, your soil test P doesn't change. So your dissolved P tends to stay pretty steady. But across the year, your field management changes a lot. Your big storms come through, whether or not you've had a recent tillage, that can cause big temporal changes in your particulate bound P. So this is for concentration, but this is what it looks like for load, pound per acre, because that's really what everybody cares about. That's what they're looking for in their Western Lake Erie Basin and all of our targeting. And so this is the same data, but now we divided the ratio of the runoff particulate bound P divided by dissolved P. And we find that the mean range, and the mean are the black lines of our boxes. So that's the average for this sampler, this field, the average, but it ranges from 1.6 to 28 times. So that means that runoff particulate P ranges from 1.6 to 28 times higher than the dissolved P. But the mean of all these means is the runoff particulate P is approximately 10 times higher than the dissolved P for load. So this is why I think, I take erosion and particulate bound P very, very seriously. And also remember that even though the soil test P, say on our high field, it was like 425 part per million Mehlich 3. But when that eroded soil goes into the drainage ditch and into the river system, into Lake Erie, it isn't 425. There's 4,000 part per million total P. So there's a lot more than just the soil test P that becomes vulnerable to dissolution once it gets into the waterways. And I'm not implying that all of it dissolves, but there's a lot more vulnerable to dissolve once it gets eroded into the waterways. And that's why it's such an issue. So again, let's scale up and say, well, what does this mean for Ohio? Give some examples. So again, we all know, we're always hear about the binational agreement with Canada. They're asking for a 40% reduction from the 2008 levels. And, my feeling, because, On-Field Ohio is a statewide tool, why don't we shoot for something like that for the whole state of Ohio? So we can run some On-Field Ohio simulations, and we compare some what-if scenarios, and we can see how things change. So in that way, we can see, well, how's Ohio doing? Because I think you'll see, well, let's go ahead. So in order to run statewide simulations, we actually developed a simulation tool that will run lots of scenarios. So it uses the exact same On-Field Ohio equations. It uses Russell 2 at each of those little green data points. So we did more than 6,000 point locations in Ohio. So we can run Russell 2, and we have all those soil survey data for all those little green points. So once we know a lot about what's going on at those point locations, we can assign crop management scenarios, and we can assign a soil test P level. Well, the soil test P levels come from a random selection from a survey we did of the soil test labs. So we had the distribution of potential soil test levels by zip code across Ohio. And so the simulator randomly chooses a soil test level from that zip code and applies it to that green data point. So we end up with a similar distribution of what you'd see in Ohio, but of course, we're not saying that that is the soil test level at that data point. We just wanted to mirror the distribution. And then for the crop management scenarios, we wanted to have a range of, some of you have probably seen this, but we wanted to have a range of crop management scenarios, a range in soil disturbance. So CMS crop management scenario 1 is just no-till, no-till. They're all bean corn rotations. So we go from all no-till, and then in crop management 2, we add a fall vertical tillage. In crop management 3, we do more of a rotational tillage where we have a fall chisel and a spring cultivator. And then in crop management 4, we applied probably something that nobody does because it's just a huge amount of soil disturbance. But we wanted to see how that would matter, what would be the result across this big range of management. Okay, so this is what erosion would look like across Ohio, given the scenarios that we just run. So again, this top left is crop management scenario 1, which was all no-till, and then vertical tillage, rotational tillage, and crazy tillage. And so it first of all, it gives you kind of a range of what to expect across Ohio, and then how do things change. And one thing we noticed from this, especially for erosion, is that in the Western Lake Erie Basin, it's hard to push erosion way up because the topography is the slopes are so flat. And then we can see that as soon as you get into more rolling parts of the state, well, then erosion starts to jump up pretty quickly, and it jumps up even more quickly as you add increasing soil disturbance. And so then it also shows you what approximately the ranges are, you know, of what we can expect. I mean, geez, you're less than 1/4 pound per acre in a lot of the Western Lake Erie Basin if you're doing no-till. And then you can be, and this is, you know, we cut this off at greater than 4, but it can be a lot greater than 4 tons per acre per year. But it kind of gives you a feel for what the erosion is across Ohio, and it is a big range. So then how does that translate to the runoff particulate bound P? So using the exact same scenario, we looked at erosion, and now it'll take a minute for this to open, but we can see what our runoff particulate bound P is. So not surprisingly, the dots kind of look the same. They have the same flow of being, you know, a lot of green dots and when you're in no-till, and then we move to black dots when we get into a lot of tillage. So what we're seeing here is that as your erosion increases, as your soil disturbance increases, your runoff particulate bound P increases. So now we are in, you know, the yellow is, you know, 1 to 2.3 part per million. Those are really high. These are nice. These under 1/2 part per million. I think Greg was talking about being concerned if you were greater than 0.2 part per million. Well, of course, that's dissolved P, so that's not unusual. But, you know, when they're talking about the soil loss going into Lake Erie, and they're talking about a half a pound to 1.5 pound per acre, well, you can see it can jump up quickly. So having said that, so these runoff particulate P levels are just a heck of a lot higher on average than the dissolved P. So I think it's a real opportunity here for reductions. So that brings up the question, is there any hope? is the 40% reduction goal achievable? And so I wanted to look at some what if examples. And so what if we reduce erosion? And so these examples I set up are, what if Ohio moved from fall chisel or vertical tillage and we moved toward no-till? And I'm not advocating that we need to move all the way to no-till. I just wanted to show some examples of, if you reduce your soil disturbance, what kind of percent reductions are possible to achieve. So this one shows that if we move from chisel, again, this is erosion. If we move from chisel to no-till, the rotational tillage to no-till, and this one, if we move from vertical tillage to no-till. That's probably a little confusing. But then you can see that, again, these are percent reductions in erosion. So even in the green, we have up to a 78% reduction in erosion. And the blue, we can have a 78 to 83% reduction in erosion. And then, of course, because there was a higher soil disturbance to begin with when you're doing rotational tillage, we can achieve a 90% reduction in erosion. So these are huge differences. And these are borne out by what we see in the actual measured data. So these aren't just imaginary, they're actually calibrated to the measured data. So what does that mean for our runoff particulate bound P? So here again, from our rotational tillage moving down to no-till and vertical tillage moving down to no-till, we can see up to a 50% reduction in runoff particulate P. In the blue, as we can see, 50 to 72% reduction in runoff particulate P. So we can get, up to 50, almost up to 90% reduction in our runoff particulate bound P by reducing erosion. And I think, every farm is different, every farm field is different. So it's really up to the farm manager. Is this something that's doable? And I hope that this data encourages you that it might be well worth it. And also, not tilling may cost less money than putting in an engineered practice, or reducing tillage may cost less than putting in an engineered practice, but you guys would know better than me. So the conclusions, what I wanted to say today is that, I don't think there's any question that Ohio agriculture is being targeted. On-Field Ohio tool has been calibrated to the measured data, and it shows clearly that farmer management matters, that reductions in erosion mean big reductions in runoff particulate bound P. And I think it quantifies, the tool can quantify how voluntary changes in management can reduce erosion and runoff particulate P. And I hope I've given some hope today that there are big opportunities for erosion and therefore phosphorus runoff reductions. And that's all I had today. So we can just take questions.
Thank you. All right, I will take over screen sharing. Let's see. Awesome. All right, thank you, panelists. Let's see. So like we mentioned, feel free to drop those questions in the Q&A box. Greg had some answered, he typed some answers. So if you can also check those out, and Bowden will be relaying some of those verbally as well for people who haven't checked the box. And just a reminder that our water quality associates, there is one in your area, especially if you're in the Western Lake Erie Basin, but we also are available to assist you throughout the whole state. So please visit our website and also our email that will go to all of us. So if you have a specific question or you're interested in a local region, we can direct you to the right location. And we're hoping to work with some farmers this summer, this spring, very soon. If you're interested in any implementing any of these practices on your farm, looking for some cost shares or anything that will help you improve your own quality, please reach out to us, because that is what we were hired for. Here is the CCA code. If you are here for credits, feel free to scan that. You'll need a smartphone. If you're having trouble with that, you can input these into the CCA website. And I'll keep that up while I hand it over to Bowden, who's going to read out some of those questions for everybody.
Thanks, Bridget, and good to be with everyone this morning. As Bridget mentioned, I'm Bowden Fisher. I'm a water quality associate, Northwest Ohio as well, but we'll go ahead and dive right into some questions. We've had some good ones come through, and feel free to keep asking those in the Q&A. So these are gonna be for all three speakers. If it's specifically for you, I'll try to address it to you, but otherwise feel free to jump in, and thanks for sticking around. So this first one's for the Statlers. How do you choose which BMPs to implement? Seems like you've had good information given to you through the partnership. What are your first steps in choosing an appropriate BMP, or what you think will be functional?
Yeah, I think the best way to kind of go about that is our BMPs kind of came with the demonstration farm itself, but that's really no different than using or reaching out to NRCS. NRCS will come out, bring one of their individuals out to your farm or however, and just kind of walk around, see what is out there, see what's available. Some of these practices, like the water drainage control structure, you can get roughly 80 to 85% of that paid off, of having some funding there through NRCS. So NRCS has a lot of these best management practices out there to be able to come to your farm and be able to see what options that you do have.
Great. Thanks, Anthony. Appreciate that response. And we'll go to the next question for Libby. At what time, and I know there's work being done on this, but perhaps you have a comment, at what time does the particulate phosphorus that enters the creeks and streams turn to DRP?
Oh, I think it starts dissolving immediately. And the question is, how long does it continue to dissolve? It'll dissolve until it reaches some sort of an equilibrium, either in the river or in the lake. And then I'm sure you've probably heard about phosphorus cycling even within the lake, because even a lot of the phosphorus that's attached to the particles doesn't dissolve until it gets into the sediment. And then if it goes anaerobic, another flush of phosphorus will come out of it as the iron minerals in the soil bound P, as the iron minerals in the soil begin to dissolve under anaerobic conditions, they release a little bit more P. And so it's just kind of a continuous process, but I do think it happens pretty fast. I mean, in a few days or a few weeks, and then it starts cycling.
I was just going to add to what Libby said. When we talk about that cycling, I mean, it's happening just like it's happening in the soil as the particles are moving downstream. And if you look at Laura Johnson's work, she does a lot of at Heidelberg University, she does a lot of the determination or monitoring to determine what the bloom is going to be by understanding what the phosphorus is going into the lake during March through June. And what they use in that counting is about 8% of the total phosphorus becoming DRP is what they use in their equations to come up with the bioavailable phosphorus.
Well, and that's true. And Laura and I have had this conversation many times, but by the time it gets to Laura, by the time it gets down the rivers and she's measuring it, a lot of the phosphorus is already dissolved out of the soil. So I wouldn't be at all surprised if at that point, 8% of the phosphorus that's left attached to the particles that she's collecting is vulnerable to dissolution, but a lot of it is already dissolved. And so she's reading it as dissolved P at their monitoring stations.
Appreciate that discussion on that topic. Thank you both. And along with the DRP discussion, this was specifically asked during Greg's session. Greg, and you did answer this via the chat, but what are DRP losses looking like between soil tests of 0 and 30 in that lower range there? Soil tests, sorry.
Yeah, you notice that wasn't on the graphic there, and that was actually, I think it was measured down to 4 parts per million, but reality is that line kind of continues down. It doesn't become 0 because we're never going to have 0 availability of phosphorus in the soil, and it's never going to be 0 in water either. But basically what you have there is between that 0 or actually very low soil test up to 30 parts per million is probably anything that's lost from a field standpoint is going to be more related to what was applied and how it was applied. In other words, if it's on the surface and we have a runoff event shortly after that, we're going to see elevated numbers. But just from soil test alone, the losses are going to be low and look similar to what that chart would extended over to 0.
If I could chime in there too, I didn't show the dissolved P today because we're just focusing on erosion, but we found that there's a linear relationship between your soil test P and your runoff dissolved P. And I would agree with Greg, this only counts if you remove the fertilizer manure applications, because you can have those short-term spikes. But your baseline dissolved P coming off the fields, if you take your soil test P times 0.003, that will tell you what your dissolved P coming off your field is. That's the slope of the line.
Thank you both for that. Appreciate the clarification on that, Greg, and then the addition there, Libby. Appreciate that. So we do have a question for the Statlers again on some infield practice here. Do you have to adjust your nitrogen rate in corn with a heavy rye cover crop? I know you didn't necessarily mention pure rye stand, but if you have in the past, or do you have any experience with that?
Yeah, we haven't really adjusted our nitrogen part of that with the rye. We don't necessarily follow the NRCS standards on the rye that we plant for a cover crop. We've found that for us in our practice in having the 5-way mix, we don't typically go much over 18 pounds of rye per acre when we're doing our cover crops, mainly because of the tillering of the rye that we get. We've learned from in the past with having one disaster field where we did that when we were first starting out, where we had such a mat and unable to really plan into that. So we're going through and pulling nitrogen tests, in the soil, knowing what we're putting in there. And every year with our manure and with the anhydrous that we do, we always are leaving strips, a couple strips out in fields to where we're able to see, where we're at, especially with the different cover crop mixes that we're doing. We've got some more uptake this past year. We did a little bit more of the oilseed radish, to be able to try to capture and keep some of that back than what we have in the past. When we first started out with this 10, 12 years ago, the only thing we put out there was oilseed radish. And we knew that we were able to cut back about 40 pounds or so of N through the anhydrous of being able to keep that. So as we continue to work with our mixes, that's kind of where we're at right now with that, but we haven't seen any real reduction on or us having to put any more nitrogen on corn after rye stand on that.
And Anthony, you had a pretty healthy rye rapeseed stand in the pictures. When was that planted?
Yeah, so most of our stuff that's corn, with our rotation, we're about a fifth wheat into our rotation. So those fields that were shown there where the demonstration farms was planted probably about the last week of August or first week of September. Typically we'll go through, put our manure on, and then we will deep rip, take out compaction, and then work that down, and then sow our cover crop right into there. So we try about every 5 years. Our goal is to get a real heavy mass of cover crop between our 5-way mix that we've got, and in the years in between that, we're putting rye or some type of cover on all the ground. But we're trying to build up our organic and trying to utilize as much as what we can on that.
Appreciate that discussion there and some good practical thoughts. We do have a question. This was given during Libby's session, but open it up to anyone who has any information on this. How are federal and state waterway designs changing to include retention ponds, thus preventing the sort of expressway design of current drainage? Anyone have comments on that?
I think that's beyond my expertise to add to the conversation today. I mean, tends to be what they try to do is actually use farm land as far as that basin to retain water in. So that causes some issues for Anthony and Dwayne when they start thinking about planning and so forth. But I'm not sure what Army Corps of Engineers has changed in any design type of things, and that would be the place to direct that question to.
Thanks for that comment, Greg. I'll go ahead and field this to you as well, Greg. You did mention it, but I think it's a good question. Although alfalfa is effective at removing phosphorus with pass-through livestock and manure, which is then placed back onto high IP testing fields, how will this fact reduce STP levels, or what might that relationship look like between application?
Well, I think the question kind of alludes to the answer, and the reality is trying to move manure to lower soil testing fields is really what we need to do, and use it in an agronomic fashion as much as we can. I think we're doing a much better job of that than what we have in the past. In fact, I would submit that's pretty widespread, that we're using manure better and using the nutrients to replace commercial fertilizer. In fact, some of the swine buildings that are put up in the very purpose of using those nutrients from a crop production standpoint. So we're doing a better job there. Where we have these high soil testing fields, it may be somebody that's landlocked, and we still have landlocked by having those high soil testing fields around them. But you know, when we talk about it overall, I think some of the data that Libby alluded to and collected, you know, maybe less than 5% are really at some of those extremely high levels. So there are places that we could go with it, and that really should continue to be the goal, is moving that manure to low soil testing fields, or using the in-crop application where we can take advantage of the manure. All of those things better utilize manure nutrients.
Great, thank you, Greg. I'll go ahead and open this up to Greg and Libby. Over time, won't practices that trap nutrients ultimately become slow release sources?
Maybe, depending on what practice is used. I mean, when we're talking about that P filter, where we have a media in that's capturing the phosphorus, actually that phosphorus is retained on the media, and it's not going to release. So the only thing that we will do there is we'll need to, you know, if we still need that filtering capacity, we need to replace that media, or some of the media that is newer engineered. Actually, you can renew it in place by running solution through, collecting the phosphorus, maybe land applying it or using it in some other way. So with that type of practice, we don't get leaching of it. We just get ineffectiveness of the filter at some point in time. What you have with a wetland is that potential that, you know, that surface becomes bound or saturated. And then there is the potential for release, and maybe Libby can speak to that piece of it, because she's worked with some of the dredge materials and some of those kind of things.
Right. Well, I've done a lot of work in my past life with P sorbents, and you know, wetlands are notoriously difficult because they may be very continuously effective for nitrogen in warm weather, but they do tend to get saturated with phosphorus, and then they're no longer effective for phosphorus. And so, as Greg says, there's some things you can do to refresh them, or if you want to be more aggressive and put some sort of a P sorbent in them, but it might be easier just to use an engineered process that where it's easier to change out your sorbent material. And then with a lot of the sorbent materials, we see a huge range in effectiveness and longevity. And then my first question always is, what is the binding mechanism that you're presuming? And what's the stability of the mechanism? And what other issues could there be with the materials? Are we sure that the materials don't have some contaminant in it or something that could cause a problem? especially when you're using an industrial or municipal waste material. And presumably that's something that gets screened for prior to its use, but I would be wanting to be sure that that was screened for before I put it on my field. And then we really can learn a lot by there are ways to measure the effectiveness and the stability of the material, and that might help make the decision whether or not to choose it.
And a lot of that current work is being done by Chad Penn, or at least in the region, Chad Penn over at Purdue, USDA ARS, is doing a lot of work with those media and has a couple of tools out from a selection standpoint if you're thinking about that P filter type of application.
Great, thank you both for the input there. We are getting close to the end of our time frame, but I'll just try to field one or two more questions. We had one, perhaps Greg or whoever, feel free to address this, but there was a question about nutrient availability and if we're not applying nutrients. So maybe you could just touch on that, Greg. If we're not applying nutrients, what's nutrient availability with our different soil test levels?
Yeah, basically when we talk about nutrient availability, I mean, and in particular, when I'm talking about phosphorus and potassium, really what we're doing through the soil test is measuring what is soil solution, what's there currently in the soil solution, which is a very tiny amount, and then what's available to replenish that soil solution during the growing season. So as long as we have a soil test that is above the critical range up to that maintenance range, the solubility or availability of nutrients isn't a problem, except for maybe when we talk about phosphorus early in the season with cold soils. That's why we may use a little bit of starter still. But you know, there's some specific situations that may lead to a temporary, but it's not a season-long inavailability of nutrients.
Yeah, I would agree with that. I think trust your soil test. I think the renewed fertility guidelines are really great. And if you're within that sufficiency zone, you should be good to go. Trust it.
Thank you both for the clarification there. I think we'll just maybe finish with this question for both Greg and Libby, but it was asked during Libby's session. I think this is particularly addressing Northwest Ohio. You mentioned that erosion rates are significantly lower due to the terrain, topography. If erosion is not where erosion is not as much of an issue, perhaps is dissolved P a bigger issue on those particular areas, or just do you have any guiding thoughts on that?
Well, that's a really good question. And yes, so while I say that on average, the particulate bound P may be 10 times higher than the dissolved P, that really isn't necessarily the case in the Western Lake Erie Basin, where it may be closer to 50-50, or the particulate P may be just slightly higher. And again, that's because the erosion is very low. And so then what would determine how that ratio comes out is the soil test P level. If the soil test P is really high and the erosion is really low, obviously your dissolved P does become your higher risk factor. So, but as soon as you get into the rest of the state, that's when you see particulate P tends to dominate. But even that can change. If you could be anywhere in the state. If you've got 400 part per million soil test P, your dissolved P is also a gigantic issue for both your particulate and your dissolved.
Yeah, and I won't add anything to Libby's comment because it's spot on. The thing that I would add to is a comment that Libby made earlier about we have reduction goals for the Western Lake Erie Basin of 40% for phosphorus. And does that need to be extended statewide? And reality is it is statewide, because when we talk about the Gulf of Mexico and look at some of the targets in relationship to reduction goals there for both nitrogen and phosphorus, it hits that 40% mark too. So the ideal of doing these things statewide really makes sense, because we have water quality issues statewide from agriculture, and it's not just the state of Ohio. We're not in this alone. You can go to any place that water congregates, and there's going to be nutrient issues where there's some agriculture in the watershed. And it's not all agriculture's fault, but it's something that just exists.
Yeah, I would agree with that.
Thank you both for that, those comments there. Appreciate it. If anyone has to jump off, feel free to do so. We just have 2 short questions here at the end that those are only 2 open. So, and Thomas Krill, you posted a question. If you could maybe clarify that a little bit, what that was in regards to before I get to it, that would be helpful. But I think this is for Libby. Do we have any idea what pre-settlement erosion levels were, or native erosion levels, or using this within our target? Any thoughts on that?
You mean before we had farming?
Yes, that was the scope.
Well, I would think that you could actually do that. You could probably get a guesstimate of that by looking at the On-Field Ohio tool and maybe run something that maybe isn't even row crop. It could be, you know, a forage crop. And but even if you look at the no-till, you can see what that the erosion is, you know, sometimes it's less than 1/4 of a ton per acre per year. But if you, but you could run some scenarios in the On-Field Ohio tool, or, you know, Russell also has a desktop tool that NRCS puts out. It's just really difficult to use if you don't know how to use it. We tried to make it a little bit simpler, but it would be, you know, certainly less than 1/4 of a ton per acre, probably a lot less. Greg, I don't know if you have an opinion on that. I've never been asked that before.
No, I've thought about that, but really don't have any thoughts how to get there. That was the most concise conversation I've heard about that, Libby. So good.
Oh, good.
Catch.
Well, you can compare scenarios. So you can compare some, you know, pre-agriculture scenarios as well.
Well, great. Thank you both. And that does conclude all the active questions we have. I'll give just a minute or so for panelists. If you have any closing thoughts, we really appreciate everybody being here. And I'll hand it back over to Bridget as panelist if you have any other thoughts. Bridget?
It looks like we're good on questions. If anyone has any questions about the webinar or getting CCA credits or want to reach out to the panelists, feel free to email one of us or reply to the post-webinar email that'll go out tomorrow. And I'll go ahead and stop the recording so we can say our goodbyes. But thanks everyone for joining us and have a great day.